Hello everyone, welcome to today's lecture. In this lecture, we are going to discuss about fiber optics. Comparing with the normal cable, fiber optics having enhanced behaviors. In that concern, first we can discuss about the structure of fiber. Here we have two important portions in the fiber. The internal portion is called core, then external is cladding, and this is optic axis. Along with this, we have one more layer which is called polyurethane jacket, which can protect the fiber from any damage. Normally, the core material having high refractive index and the cladding material is having low refractive index. If you send any external light through the fiber, it should obey the total internal reflection condition. So, we should understand what is total internal reflection. For that, if you take two mediums, one is denser medium, another one is rarer medium. Assume this is the plane, the ray of light is going to travel from denser medium to rarer medium. It can undergo refraction in this condition, and this is the normal, and the angle between the incident ray and normal is angle of incident. Most of the peoples, they are having misconception. They could choose the angle between the incident ray and the plane as incident angle. This is misconception, since this portion is called glancing angle. Now, if you increase the angle of incident, the angle of refraction also increased. So, here also we have to measure the angle of refraction from normal to refracted ray. So, if I increase the angle of incident, angle of refraction also gradually increases. Furtherly, if I increase the angle of incident, the angle of refraction is 90 degree. That angle is called critical angle. The critical angle plays very important role in the total internal reflection. The exact definition for critical angle is, for a particular angle of incident, angle of refraction is 90 degree. That angle is called critical angle. Above the critical angle, if the angle of incident furtherly increased, it gets reflected within the same medium itself, that is denser medium itself. That phenomena is called total internal reflection. So, for all fibers, total internal reflection plays very important role in order to enhance the efficiency of output. In this concern, we can derive the expression for critical angle. Expression for critical angle. So, before deriving about this, we can have a recap on laws of reflection as well as laws of refraction. For laws of reflection, if you assume the ray of light transfer from one end or one medium, if it gets reflected like this, here the law is, law 1 is the incident ray, reflected ray. So, this is called incident ray and this is reflected ray. Incident ray, reflected ray, normal, all lies in same plane, that is law 1. The same way law 2 is the angle of incident is equal to angle of reflection. Similarly, we can discuss about laws of refraction. Again, you can assume the ray of light is going to travel from one medium to another medium. if it is refractor like this, again law 1 is similar to laws of reflection. The incident ray, refracted ray, normal all lies in same plane, whereas law 2 is very important, which is applicable in total incident reflection also. That law is called Snell's law. According to Snell's law, the ratio of sine of incident angle to sine of refracted angle is constant, and this is called refractive index. Refractive index. So that refractive index plays very important role in the fiber optics. As we mentioned earlier, the refractive index of core is high and refractive index of cladding is low. Then only it can obey total internal reflection condition. Now coming to the expression for critical angle. So according to Snell's law, so here the refractive index of denser medium is N1, the refractive index of rarer medium is N2, and you can write the equation as N1 sin theta I is equal to N2 sin theta R. From this, sin theta I is equal to N2 by N1 sin theta R. As we discussed earlier, for critical angle condition, refraction must be 90 degree. So for 90 degree, it can undergo total internal reflection. So theta I is equal to theta C. In that concern, sin theta C is equal to N2 by N1 sin 90 degree, and we know sin 90 is 1. Then we can have sin theta C is equal to N2 by N1. Theta C is equal to sin inverse N2 by N1. So this is the expression for critical angle. And based on this, we can derive the expression for numerical aperture and acceptance angle. In other words, we can say this is principle of light propagation through fiber. Or we can say principle of light propagation through fiber. So first we should know what is numerical aperture. See, if you take any fiber, the opening portion is called numerical aperture. This portion is called numerical aperture, in which the ray of light can incident so that it can undergo total internal reflection. And acceptance angle is the light enter in the one end of the fiber. If it enter at a particular angle, then only it can undergo total internal reflection. That is called acceptance angle. So in that concern, we have to derive expression for both the numerical aperture and acceptance angle. For that, we can assume again a fiber. The fiber, this is core portion as we discussed earlier, and this is optic axis, and the core having refractive index N1, and this is cladding. It has refractive index N2. Assume that a ray of light is going to incident on one end of the fiber, say that point is O, and the refract index of surrounding or air is n naught, we can assume. So, AO is the incident ray. Then by obeying total internal reflection condition, the ray can be refracted and it meets the point B, in which the angle is 90 degree, and after that it undergoes total internal reflection condition, and this is angle of refraction. As we know, alternate angles are equal. In that concern, you can mention this is refracted angle and this is also refracted angle. In the same way, this is the AO is the incident ray, OB is the refracted ray, but for point B, OB is the incident ray in which the angle of incident is 90 degree minus theta I. So, at point B, 90 degree minus theta is the angle of incident. Now, we can apply Snell's law at O. So, applying Snell's law at O. So, we can write NO sin theta naught is equal to N1 sin theta R. In this, sin theta O is equal to N1 sin theta R by N naught. You can assume it is as O or not, that is up to us. And here, instead of sin theta R, you can write sin theta naught is equal to N1 by N naught root 1 minus cos square theta R. Since we know that sin square theta plus cos square theta is equal to 1, from this sin square theta is equal to 1 minus cos square theta. If you need to find out sin theta, which is root of 1 minus cos square theta. So, in that concern, instead of sin theta r, we can substitute 1 minus cos square theta r. We can assume this is equation 1. In the same way, we can apply the Snell's law at point B. And as we mentioned earlier, here this is the incident angle. So, N1 sin 90 minus theta I is equal to N2 sin 90 degree. Since at B the angle is 90 degree, and we are all know sin 90 minus theta is cos. So, N1 cos theta I is equal to N2 sin 90. From this, cos theta I is equal to N2 by N1, and here this is theta I and this is theta r. Alternate angles are equal, so you can represent this as theta r also. This is equation 2. Substitute the value of 2 in 1, we can have sin theta naught is equal to N1 by N naught. Instead of cos theta r, we can substitute N2 square by N1 square. So, simplifying this, sin theta naught is equal to N1 by N naught root N1 square minus N2 square by N1 square. Furtherly simplifying this, sin theta naught is equal to N1 by N naught. You can take root, so you can write this as N1 square, so N2 square by N1, and by cancelling this, we can have sin theta naught is equal to root N1 square N2 square by N naught. From this, theta naught is nothing but acceptance angle. So, theta naught is equal to sin inverse root N1 square N2 square by N naught. Here N naught is the refractive index of air. For air medium, N naught value is 1. So, in that concern, theta naught is equal to sin inverse root N1 square N2 square. So, this is the expression for acceptance angle. Then followed by, we can discuss about numerical aperture. Numerical aperture is nothing but it is the sine of acceptance angle. In that concern, we can have numerical aperture equal to N1 square N2 square. So, these tools are very important for to understand any fibers principle, and based on this we can discuss the losses associated with the fibers. So, if you are using any fiber, definitely there will be a losses, and there are three types of losses. So, losses in fibers, the types are material absorption loss, scattering loss, and bending loss. See, the material absorption loss, it is furtherly classified into three categories based on the material which is used for the manufacturing of fibers. It is extrinsic absorption, intrinsic absorption, absorption by atomic defects. So, while using the fibers, there is a chance from the extrinsic material. If it is absorbed, then there will be a loss of output. Intrinsic absorption loss takes place during the manufacturing itself, or while using because of continuous usage also there will be a chance for the intrinsic loss. Then absorption by atomic defects also takes place during the manufacturing if there is any defects during the manufacturing. The scattering loss takes place because of the continuous usage, and which obeys the Rayleigh-Jeans law. So, normally Rayleigh-Jeans law states that the amount of scattering is inversely proportional to fourth power of wavelength. So, that is the second type of loss, and third one is bending loss. It is also furtherly classified into two categories such as macroscopic bending, microscopic bending loss. If you take any fiber, in which the radius curvature of the bending is greater than the diameter of the fiber, macroscopic bending takes place. While bend the fiber, there will be some changes in the diameter. So, the radius of curvature is greater than diameter of the fiber, macroscopic bending takes place. Whereas, the radius of curvature is lesser than the diameter of the fiber, then microscopic bending takes place. In order to overcome these limitations or to avoid this loss, we have to extrude the material So, extruding process is nothing but simply we can squeeze out. So, by squeezing out we can minimize the losses which occurs due to bending loss. Mani sir,